Gamma ray bursts are these giant explosions that occur off in distant galaxies, well outside of our solar system. And they either occur from a binary compact merger, which is where we have either a neutron star and a neutron star, or a neutron star and a black hole coming together and colliding, or the core collapse of a massive star, a giant star imploding on itself. And from it emits a burst of gamma rays, and gamma rays are the highest energy form of light.
The GW partnership with NASA is a huge benefit for us. It allows us access to some amazing students like Nick. Here at Goddard, we don't actually have a student base, so we have to look to the nearby universities to actually work with students. And this is particularly important for these types of projects. Not only is it great technology demonstration, but it's a great training ground for the next generation of scientists.
The Compare project is the prototype of a gamma ray mission concept, which aims to bridge a gap in data that exists in gamma ray astrophysics. Currently, we can use data from Fermi Gamma Ray Space Telescope, and on board Fermi are two detectors, one that's sensitive at low energy gamma rays and one sensitive for high energy gamma rays. But right in the middle there is that sweet spot that neither instrument is necessarily sensitive to, which is why we need an instrument to cover it.
We're trying to explore the cosmos in a new way. We're trying to look at very high energy explosions in the universe that are only accessible in this very unique range in the gamma ray regime. So we're trying to show these new technologies at this stage such that we can prove to ourselves and prove to the community and prove to NASA that this new technology can work on a much larger scale.
When you work on Compare, you are working on the technology that you don't know yet if it's going to work or not. You are trying to prove that this technology is viable, that you will be able to put on a space telescope. So what Nick is doing is basically trying to convince NASA that it is worthwhile to send this gamma instrument and that we will actually be able to do important physics with its instrument.
We went to Fort Sumner, New Mexico for the launch. It has a very small population and it's a lot of desert, so it's a good launch site. The balloon looks like a giant plastic bag, and initially it looks large, it looks long, but as it goes up in the atmosphere, it enlarges and it blows up to the diameter of a football field, so it's huge.
So we do this on a small scale first on a balloon-borne mission because it gives us cheap access to space, so we can observe the cosmos on a very small scale. And it's a way to have the instrument fly in a space-like environment but come back down to Earth, and so we can refurbish it, make changes, and then fly it again.
The coolest part of working on this project specifically was seeing how a project like this develops. From simply just putting together and screwing in stuff to actually the last day having it fly, getting it off the ground, and seeing the data that took.
When you are a physicist, there is three main pillars. You have an idea of what you want to observe, you build your instrument, you collect the data, and you interpret the data. And a good physicist has to have a good knowledge of those three fields. And here, the students working at Goddard have a very good expertise in the three fields, but especially in instrumentation.
The partnership between GW and NASA has provided me with incredible opportunities to work on hands-on instrumentation here. I learned that I enjoy instrumentation more than analysis, and I wouldn't want to just do a project that is purely analysis. So getting this opportunity to actually come in and work and collaborate with people at NASA and from all different universities with one common goal has been incredible.